Hello, everyone. Thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on KART 25991 Lightning Research Program for Fastener Sparking Threshold Database. Before we start the presentation, let's review the user interface. On the top of your screen, you will see a bar with 4 options for you to click. To ask questions, please click and open the Show Conversation option. This will show the meeting chat, and this is where you may ask any questions you have during the presentation. At any time during the presentation, you can submit your question. Your question will be placed in the queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. Now on to today's speakers. Cody Weber is a principal scientist and co-owner at Electromagnetic Applications, where he leads an E3 consulting and complex modeling team. Billy Martin is one of the world's most renowned experts in EMC, HERF, and lightning standards, testing, design, and certification. Brock Milford is a HERF and lightning engineer for NIAR's Environmental Test Lab, where he's assisted in development of the ignition source detection test methods NIAR uses for fuel ignition source testing. Ernie Condon is a senior research engineer at NIAR with 40+ years of experience in the aircraft industry in the design, certification, and testing of aircraft. And our last speaker is Jim Dellinger, who is the NIAR Works ETL Business Director with 33 years of experience in technical and management positions with emphasis on mechanical systems and product development. Without further delay, I will pass it off to Jim to get us started.
Good morning or good afternoon, ladies and gentlemen. Thanks for joining us. Again, I'm the Jim Dellinger, the director here at NIAR Environmental Test Laboratory. NIAR was established in 1986. We have 15 laboratories, and Works has 3 of those laboratories. One of them is the Environmental Test Laboratory, which we'll speak mostly about today in my presentation, but we also here at Works have a full suite of engineering design folks, and we also have a Part 145 certified maintenance and repair and overhaul facility. And all the things we talk about, NIAR is happy to help you or consult with you on things that you may or may not be familiar with. Our staff, we have 20+ DERs on staff here at Works. Billy and Ernie are part of that, and then Brock is working towards his as well. We have over 200+ engineers in the electrical, mechanical, and physics arenas. And then we have many test engineers, test techs, and mechanics throughout the Works organization. We have many subject matter experts that work on the DO-160 environmental laboratory conditions, sit on those committees, help rewrite the areas that need attention to, as long as 307, which are just PEDs, and 362 on command and control, unmanned detection and avoidance 365, 227 non-rechargeable lithium batteries. And then, so our expertise is setting on those committees and working with the communities to make sure that they stay up to speed. And we also sit on the SAE A2 committee, AE2 committee for lightning, and AE4 for HERF, and then the A22 for fire. Billy, Ernie, and others here have had many, many years of experience working with the FAA in the HERF and lightning and the fuel systems and PEDs. And so these are very specific areas that we work in, and we have a tremendous amount of knowledge. And then for the laboratory, we do test plans, procedures, design fixturing, then we do test setups, we do conformity of test setups. We do obviously the testing. We have the capability to do video and in-person witnessing, and then analysis and also reports. So laboratory testing, so all the ones that we talked about on the other page. So DO-160 is where we live and breathe with a lot, but everything's adjacent to DO-160 and 810 for the environmental side of it. For mechanical, we test to, and then Mill Standard 461 from DO-160, and then we have the full suite of 227 for the non-rechargeable lithium batteries, and working towards 311, which is the rechargeable lithium batteries. We have the ability, I break these out because a lot of people want to know about them. So the high intensity radiated fields in the laboratory, indirect effects lightning in the laboratory, and then the direct effects lightning in the laboratory. We have those full suites. We have full vehicle testing for lightning transient analysis, and then the low-level swept currents and low-level swept fields, PEDS, EMI, and precipitation static or P-static. All of that can be on the road if you were to need it, or we also do that here at Wichita at our facility. The guys that are sitting in here to my left, to my right, Billy and Ernie and others, teach courses for us. And so full suite of DO-160, HERF and Lightning, workshop, systems lightning, cybersecurity. So we have those classes available for folks to attend, and I highly recommend it. If you want to learn about those things, we have the right folks here to teach those classes. And we do those in person, we do them virtually, we do them also for companies as a private class. So again, NIAR has been around for a while, the National Institution for Aviation Research. Overall, we're here to help you with your problems, solve your problems, and so come please work with us. Thank you, and everybody have a great day. I hope you enjoy the next portions of the presentation. I think you find it very interesting. Thank you.
Thanks a lot, Jim. My name is Cody Weber. I'm a co-owner of EMA and principal scientist here. EMA stands for Electromagnetic Applications. We've been providing EME consulting and simulation support for aerospace companies for 45 years now. We have two software products that we develop internally, EMA3D Cable and EMA3D Charge. We use these to analyze problems and solve real industry problems relating to electromagnetics that our customers find very useful. We have expertise in a plethora of electromagnetic environments, including lightning, both direct and indirect effects. Today, the focus will be on mostly direct effects, but it certainly has to do with lightning coupling. And then we'll also provide services in HERF for LLSF, LLSC, EMI, EMC, RF interference, and many more. And with that, I'll pass it off to Billy to give an introduction for the 954 regulation, its history, and why we went about doing this KART program. Billy?
Okay, thanks, Cody. And again, I think the partnership, as Jim talked about, NIAR is really unique in the world and all the different things they do. And one of the things we do explicitly is we partner with industry. So it's very much different than most laboratories in the fact that, yes, we have to keep the lights on. So yes, we partner, but really we're here to assist industry in the development of standards, in the development of designs, and to help industry go about meeting compliance. Because again, we all have vested interest in the safe aviation and safe aircraft. We all are in the safety business. So what happened several years ago, airplanes started to have issues with fuel and lightning interaction. So this chart just kind of gives a history of that, starting back a long time ago with the Boeing 707 back in 1963 was really the first one recorded. Now this doesn't deal with military aircraft. They use a different type of fuel and a different operational characteristics. But as you can see, back in 1963, one of the things that all these have in common is they all start with the word B, right? So back in 63, there was a 707. What really drove requirements, and we started up into 76, the FAA wrote a rule trying to prevent ignition sources as primarily driven around what we call 25954. It says prevent catastrophic effects from lightning on the fuel system. So in other words, don't go bang, okay? Then in 96 and 2001, there were some additional flammable issues with the 747 and 737 that resulted in some inerting research, but it was considered to be really impractical to institute. And then the big one that happened was in 96 when the TW800 exploded over the Long Island Sound, which, and everybody seen that, which resulted in the 25981 rule being published. Now, that rule being published had a tremendous impact upon certification, really. Boeing spent about $135 to $140 million on the 787 certifying to that one single rule. Okay? And as a result of that, industry said, hey, this is made out of unobtainium. With the way this rule is written, we cannot comply with it. Okay? So there were policies and exemptions written, and I was the chairman of the ART committee that rewrote that rule and provided inputs or made suggestions for rewriting it. The FAA rewrote it, but made suggestions on how to rewrite that to make it feasible and practical to do it. Now, in 2006, it was updated for flammability as well in Amendment 125. So let's go forward. So as a result of this, at the time, I was the chairman of the National Lightning Committee for the SAE and AE2, and we have a task group that is currently writing a document called ARP 6205. Now, as part of that research that was being done and to try to help industry, we came up with what we call a KART program. Now, everyone always asks, what is KART? Well, in the state of Kansas, Wichita, Kansas is considered to be an aviation cluster. In other words, we have a lot of industries right around this area: Boeing, Airbus, Cessna, Textron, Beech, a lot of aircraft companies, and therefore a lot of support for those aircraft companies in Wichita. And Kansas is considered to be an aviation cluster. Well, the state of Kansas helps support these programs, and they do, or these companies, and they do that through a program known as KART, Kansas Aviation Research and Technology Growth. So every year, the taxpayers of Kansas provides these companies with seed money, which they must match and increase to develop programs to advance safety and to do research into various issues of aviation. Now, NIAR is probably their real claim to fame is in composites, and they control, and they're the host for the Composite Materials Handbook 17, which is utilized to certify all composites that are used in aviation. So I proposed a program for KART in which we would develop a set of databases, basically, for sparking thresholds of fasteners and fuel tanks, because that's part of the issue with 25981 and 954 is the amount of testing that must be done for both nominal installations and for sparking thresholds of faulted installations. So we have this program set up in two phases, or actually three phases. One is to develop this material database for metal aircraft, to do a development program for the modeling, which Cody will speak about, and then to do the same thing with composite airplanes. And so a lot of people say, well, what is the advantage of this? Well, the first advantage is that this is really overwhelming when you look at this and you decide, hey, what am I really supposed to do? Because there's not a whole lot of guidance out there. So the first thing it was we were going to run through a program. We have a wing. We're trying to determine the sparking thresholds that would be utilized for certification of the fasteners, and how do we do the modeling for that for validation. So we went and got a wing. It was donated by Textron. It was a Beech Hawker Horizon wing. We took half of it and we cut it up literally to put the data, to develop the data for the model. And then we took the other half of the wing and we did validation testing. And that test data results and all is located in this link that you see right here in the test report. So the goal there was to try to bound this in somewhat, to say these are the typical faults that you would have to look at. You must do fault tolerance. So when you do that with fasteners, for example, typically with lightning, we have two ways to meet those requirements, right? We do it through electrical bonding of the fastener to the skin, and we do it through sealant in case you get outgassing. So the goals of the program was to kind of describe the process that you would go through to do this certification, and to also develop a database on fasteners with certain sparking thresholds. And then the third thing was to try to validate the model, because in the past we've always done, EMA has been around a long time and they do phenomenal work, but there's not a lot of data made available through public domain on how that program actually produces information that could be utilized. So since this is funded by taxpayers, it becomes a public domain after a certain period of time. So one of the outputs was simply to say, how does the modeling match up with the actual validation? And I think I'm sure Cody will talk about it, but it convinced me and it made me a believer in the modeling because it matched up very well. Now we have some additional research plans to try to do this exact same thing with composites. We had to prove first we could do it with metal, because really, if we couldn't do it with metal, we certainly could not do it with composites. But I think the program has been a resounding success. We are attempting to get it linked into the 6205 ARP, in which case then it becomes advisory guidance material that can be utilized for certification. Now, you certainly couldn't use it directly for similarity, but it will help you in regard to trying to bound what all you do have to do. You don't have to go do a bunch of research and things to determine exactly what you do have to test. This helps you in that. So I think it's been a resounding success. I'm no longer either the chairman of the committee or the director here, but I do know the intention is to try to expand this into composites and put a bow around it, reference it in 6205, and allow for industry to utilize this data to help put some boundary conditions on this on this 25954 rule. So with that being said, I think that's kind of the introduction of the program, what KART is, what we do here, kind of what the data details, and these guys will get into more detail about exactly all of the information contained. So with that, I think it's Ernie, right? So I'll pass that along, and if you have some questions for me, we will try to answer them at the end.
Welcome, folks. Ernie Condon, as noted earlier, worked with Billy for a long time, and he's quite the character, legendary to say the least. So it was thanks, Billy. Couple of slides here on coupon design. NIAR developed a design for the coupons, and that was in cooperation with the OEMs and SAE, AE2. They took that definition and supplied it to 5 of the OEMs here in Kansas, and they helped us with building the coupons. That gave us the necessary input and variability that we needed for these coupons. 2 different configurations were used for the coupons. In some cases, they were 1 rivet per joint, and in other cases, there were 4 rivets per joint called quad fasteners. The main reason for the single is just to characterize the 4 versus the 1. The quad is actually more representative of an aircraft installation and was going to be where we would get a real data, but they wanted to characterize it compared to a single fastener anyway. Again, the fastener types and installation methods were chosen with input from the OEMs as far as expected variabilities and the like, and also with the SAE AE2 Lightning Committee, so that we'd have an industry consensus when we did that. We wanted it to be useful data. It wasn't just a science project. We wanted it to be useful. The ARP 5416 recommends that you do 3 test samples for any ignition test that you do. So in order to accomplish that, when we built our coupons, we actually had 4 pieces of aluminum connected in series. So we wound up with 3 joints per test, all with identical currents. And so that gave us the 3 joints per coupon that way, and we met the needs of that triple test. These tests, there was, when we were working with the supplier or the manufacturers, we found that the variability and confusion with sealant was too much, so we did not include that in our experiments. Next slide. Okay, on the there you can see a picture of the coupons. You can tell there's four pieces of metal in each case, and they're connected in series. And again, our generator is very much like an ideal current source. So having multiple joints really did not affect the current or the wave shape. It was very robust generators to do the test. The ones with the 4 fasteners, it was chosen that we would only have one of those have a fault installed because that was more representative of what you'd expect on an aircraft. It was low probability that you'd have a cluster of faulted rivets on an airplane, so we thought that was more representative. The fault conditions were chosen to meet the needs of 981 and 954 because those require fault tolerance and consideration of fault conditions, so that's why we chose these. Types of faults, 6 different types of fault conditions were included. They're listed here. Straight gap is where the hole is oversized and you have essentially an equal spacing all around the fastener through the hole. A gap under a head is where, to facilitate that, shims were used in installation and then removed after installation, so you would get a characteristic gap under the head. The gap under the collar was similar, done with shims at installation to simulate that kind of fault. A scratch is a certain size, 5 thou wide, 5 thou deep, and 1/2 inch long scratch in the aluminum surface of the coupon underneath the fastener. A burr is where if the drilled hole was drilled too quickly, you can get burrs on it. In some cases, that was simulated by just applying a shaving in the hole when it was assembled. And then under torqued is pretty obvious on the high lock and high light kind of fasteners. Those require a torque setting, and if you under torque those, that was the fault that we simulated there. And that's it for my slides. Next, I believe, is Brock. Yes. Okay.
Thanks, Ernie. Let me slide over here. So this is a pretty interesting project in that we had 5 OEMs all build coupons to the environmental specification document. And that specification document allowed the manufacturers to use their own processes to build the coupons. We specified the faults, we specified the size and the fasteners to be used, and they were allowed to build them as they currently conduct their processes, because that's one of the control variables we were looking at. So when we got them, we had to basically try to characterize the variance between manufacturer coupons, and this was quite the task. Big thanks to Yulia and Alyssa and Michelle for working that. Ways we did that was we did a DC resistance check, and we actually have the plot on that on the side there. A couple of you can see a lot of the variance there. A couple of those were non-conductive fasteners, where they had a non-conductive coating on the outside of them. Another thing that we could check for manufacturer variability was paint thickness and the energy delivery. Basically, we characterized the current values that we got during testing to make sure they all fell within a bounds. DC resistance is not the same as a high current delivery, so if there was something different with the build and the coupons, the hope there was that we would see a vastly different current response, and we did not actually. One of the biggest problems we had with this project was anomalies between the different coupon builds. We had several mistakes where I think one, we had different panel thicknesses on the top panel. We had an issue where for the oversized holes, we had a tolerance mix-up where our interference fit and our transmission fit tolerances overlapped. So one manufacturer drilled things the same holes. So we did catch a lot of that ahead of the test with our pre-test checks, and we had some variance in the test results, and then we dissected the coupons at the end of it, and were able to kind of find what happened. So our team did a really good job of adjusting our results and normalizing for those anomalies and producing some good data from this. Next slide, please. So testing approach, we use the methods from SAE ARP 5416 and the waveforms for ARP 5412. This was basically a conducted current test using the component A 6.9 or 6.4 by 70 waveform. For our single fastener installs, which were the nominal installations, we typically started in the 5 to 10 kiloamp range. For the quad fasteners, those take quite a bit more current, so we had to go all the way up to about 100 kiloamps on that. Component B and C are direct effects waveform components. C is kind of like a continuing current component, and it's difficult to apply that in a scaled fashion. So what we did for those two is we took the charge transfer from the scaled B and C and basically put that together as a lumped parameter and applied it as a exponential waveform. And that was basically scaled up and down. So it was only two waveforms applied. We applied those simultaneously, the A and the BC component. We use the light source method for everything. So basically what we do there is we take a digital camera and we use a camera verification to ensure that that digital camera can capture the light from a 200 microjoule spark. 200 microjoule is the minimum ignition energy for all the different components that make up typical aviation fuel. That's the standard for ignition source testing. You can either do it with a camera source or you can use that 200 microjoule source to calibrate a substitute ignition ignitable mixture, like a hexane mixture or an ethylene mixture. In this case, camera method is a little bit easier, especially since we're dealing with the same kind of coupon, same coupon size, fixed distance from the camera. And then we also use differential voltage probes to take measurements across the joints. That allowed us to kind of see, basically, if you get a high voltage buildup characteristic of something that has either non-conductive or some sort of non-contact, also allowed us to capture internal sparks. And basically what you'd see there is kind of kind of like a ripple on the leading edge or something along those lines. And so sometimes you can have the head and the collar of the fastener contain a spark within the hole that does not cause an ignition source. So that kind of helped us detect stuff that we couldn't necessarily see with the camera method. Next slide, please. Quick couple pictures of our setup here. So the lightning generator is the box there. You can see the wave shaping network up top, and basically it's just a dark box. We slid those coupons through there and passed the current through the coupons. We've got 3 different groups of fasteners for coupons, and that's kind of a requirement of the testing that sparking is kind of a statistically driven event, so you are required to test multiple configurations of each installation. You can see the differential voltage probes there, and we use 2 different scopes to capture the A and the BC. And the camera setups, monitoring both sides of the test article that we trigger remotely. The next slide, please. So kind of what we're looking for on these is for the nominal fasteners, we're looking for the minimum sparking threshold. So we want to find the minimum current value at which the nominal installation does not spark. So you kind of have an installation guide. And then for the faulted fasteners, it's the maximum non-sparking threshold. For some of the fastener installations, we were able to go up to about 100 kiloamps, and that's more than enough, and that's kind of where we drew the line. If it's past that, it's probably a pretty good installation. Next slide, please. So kind of what we found, Majority of the sparks came from fasteners with non-conductive coating. Not surprising, riveted fasteners performed a lot better. Riveting causes the metal to expand and make contacts with the edge, and if you don't have a gap and you've got good surface contact all the way around, no spark. Pre-test bonding resistance measurements had no correlation with sparking performance. So key finding of this, and this should be known, is 2.5 milliohms is not a design target. We did have some issues with the manufacturer anomalies that we discussed earlier. Had a couple oversized and elongated holes. We had a hole size that was too small for what the transition fastener fit was. Essentially, like I mentioned earlier, we were basically able to dissect all these coupons, and we did not allow any of the anomalies to skew our results. In some cases where we had wrong fastener installs or something like that, we could basically shift those results to another category. So we just had less data samples in one set and more data samples in another set. Next slide, please. So part of what we were looking for on this was to determine what factors had a great effect. So as I mentioned earlier, obviously riveting fasteners provide the best performance. Fastener head type did not matter. The diameter of the fastener, surprisingly enough, did not produce significant results. The fit type, transition fit, caused more internal sparking, but minimal correlation to external sparking. The coating was a big driver. That was the most statistically significant driver in the reduction of sparking, is using a conductive coating versus a non-conductive coating. By looking at the fault types, the burr and the gap under collar caused the most sparking relative to the rest of the fault types. Obviously, more fasteners means you've got a better current distribution across the fasteners and less risk of sparking. And one of the also interesting findings of this is for our controlled manufacturing variants, which we can trace back to the manufacturers building the same coupons with their own processes, that did not impact the spark threshold, which is good news. The anomalies did cause some sparking. Most of it was internal, which would not be a ignition source by the test, but it is kind of worrisome from a design perspective. And I believe that's the end of my slide, so thank you.
All right. Thanks, Brock. So for the, Brock, can you mute your?
Yes, working on that.
A little bit of an echo. All right, that's great, thanks. So the next part that I'll talk about, Billy mentioned in the opening that there's a simulation phase associated with this project. And the reason that we do simulation is part of the fuel system environment definition. And so what you have to do is you have to establish the current level, the amplitude and the waveform that could exist at every design interface within your fuel system that you will have to evaluate if ignition will occur or not. And this can be a major step in the 954 certification process. And you have to do a grouping of your components in a way based on fastener type, diameters, locations, whatever it might be, that you can put these design features together in a way that you don't have to understand every current at every fastener within your fuel system. That's not practical to do. So the way you group these features together can matter a lot. And it can really help to reduce the number of measurement locations or simulation probe locations that you have to establish during your environment definition. And within the guidance material 6205 that we're writing right now, that is very nearly finished, you can specify your lightning environment for your fuel system by testing, analysis, or similarity, or of course, some combination of those. And with discussions with NIAR and other programs that we've worked on for 981 and 954, really, we feel the best solution for setting your lightning environment is a combination of testing and simulation to use those harmoniously. And I'll talk about what that means and sort of that selected demonstration approach for the KART project here. And kind of at a higher level, what the NIAR team has shown to this point is sparking threshold database that they've developed for typical fastener installations on metallic wing aircraft. As part of that, you have to understand when you go to do your injection onto those coupons, what will be the appropriate lightning amplitude and waveform that you can expect to see during a lightning event. And so this is really dedicated to that understanding. What is the appropriate waveform and amplitude that you would expect to see at a particular design feature location? For all of this analysis, we use our internally developed product, EMA3D Cable. It is a very mature software platform. It's well suited for lightning, HERF, EMI, EMC interaction problems on aerospace vehicles. We have the ability to model full vehicles. We have the ability to model very fine details focused on, small fuel system interfaces. We have the ability to model complex cable harnesses at the same time as our full aircraft. We have a transmission line solver integrated with our full wave 3D solver. And this is what we use for this analysis. So when doing the lightning environment definition process, there are some key steps. First off, you have to sort of establish a validation plan. What model and what test specimen do you have available to do analysis on? Do you have an entire aircraft that you're going to use for your environment specification? Do you have sub-assemblies of fuel system components? Do you have a wing that's available to do this assessment? And as Billy mentioned, there was an aircraft that was donated and we were able to use as part of this evaluation for this KART program. And we took half of one side of the wing and we used it for resistance measurement, and we used the other side for a full wing lightning injection evaluation. And that's what's shown here, is that the one side of the wing that we rigged with an RCS and outfitted with probes so that we could do current measurements throughout the wing structures of this particular wing. An important thing to mention is that this aircraft had the fuel systems removed, and that would certainly be an important part of the process. But since the KART program was focused on fastener interfaces for mostly structurals components, we thought it was a good representation of what we were after as part of this program here. So once you have defined your aircraft specimen and the model that you will be using for your environment definition, you have to have some way of representing that geometry within your simulation. And in this case, we had CAD models that we were able to import and use and prepare the geometry for our CEM simulation, CEM being computational electromagnetic simulation. After you have your geometric representation, it's very important that you have good data for your resistivity of materials and interface resistances between components. And so that was a big step in the process I'll talk about next, is being able to establish what reasonable contact resistances might be between main structural components. And once you have built your model and performed simulations according to your attached-detached scenarios that are appropriate, you have to be able to compare your simulation and test results together. And that's both in terms of amplitude and waveform. And so once you have done all that, there's always the touchy subject of establishing margins. So I'll talk about each of these a little bit more that we utilize for this program. So for the resistance measurements, what we did is what I shouldn't say I didn't do this at all. I just kind of said, let's make some key measurements at these interface locations between ribs and skins, ribs and spars, skins and spars, and basically every structural type of representation we had within the wing. The NIAR folks did a great job of cutting samples from that opposite wing and then performing resistance measurements to gather inputs to improve the fidelity of the simulation model. Now, Brock, one of his key points that he mentioned for establishing sparking thresholds was that the pre-test resistance had no correlation to occurrence of ignition event. But I can tell you for sure that the resistance does impact the current distribution. So whether or not it results in an ignition event, we can't say, and resistance may not strongly correlate to that, but it does have a big impact on the amplitude and wave shape of current distribution throughout the wing. So it's very important to understand what kind of resistances and interfaces might exist within your fuel system when doing analysis. And so we collected a lot of data using these coupon samples at these primary structural interfaces and used those directly as inputs for our simulation model. And a lot of time was spent understanding the ranges and some sensitivity associated with those resistance values. For the actual testing, we created a test plan that utilized the entire wing. We measured magnetic fields with BDOT probes, both exterior and interior for structures. And then also we looked at currents on attached braids, main attached brackets, and an interior wire that we added that would be somewhat representative of the resistance of a fuel pipe or a hydraulic pipe inside the wing. So we had a test matrix that we looked at. One of the scenarios was a wingtip attachment and a root detachment or current exit. We also had a case where we did a fastener injection that would be representative of a 2A attachment zone. And we also did an attachment to one of the brackets on the leading edge and conducted current across the wing. For this particular wing, there's no engine mounted on the wing, but there are certainly scenarios where the engine design is such that it's mounted on the wing. And so we wanted to conduct current across one of the ribs for that particular type of design. So here's a summary of data that we have for all the measurements we did, both with a test result and then a simulation result. And then this is just comparing the magnitudes. So on the left hand, or the y-axis of these plots, we have the experimental value. And on the x-axis, we have the simulation value. And what we do for this is sort of show a correlation between the two over a logarithmic scale of amplitude. So the low end, if we're looking at BDOTs, is 10 amps per meter, higher end being on the order of 5,000 amps per meter. So it shows a very wide range of amplitude for this correlation. When you see a data point shown in a green diamond that lies very close to a red line, that means that the amplitude is very close to each other between the test and the simulation. And we also add plus and minus 3 dB lines around this to show the correlation level between that particular amplitude of test and simulation result. And for all of these data points that we had, we got correlation within 3 dB. And I say we were looking only at structural currents for this evaluation because that's all we had available within this particular test specimen. But it correlated well to the goal of this KART program, looking at structural interfaces with fastened joints. Here's some samples of the waveforms. And so this is looking at magnetic fields outside on the wing, magnetic fields measured along ribs at interfaces between skin and spar or rib and skin, and then also some interior current locations. And so we have 44 different plots like this. And if you're going through your certification program for 25954, certainly you will be asked about peak magnitude establishment for your environment. And if you're doing a validation, that's a correlation between simulation and experiment like we showed on the previous slide. But you'll also be asked about the waveform. And that has to do with the action integral or energy content associated with the current flowing through a particular area. And there's different beliefs and philosophies about how you would do a validation or establish that particular level. There's good information in ARP 5415B that talks about waveform reduction and how you should consider the different waveforms and do that evaluation. So I refer you to that for a deeper explanation. But what we're seeing in all of these results is a very close correlation between the test and simulation, both for amplitude and the general shape of when the peak time occurs and what the T2 is like for it. Now, not all of the test results here have T2s. We didn't have the time to go back and do additional testing to carry them out for a long duration, but everything that we were able to acquire had a very good correlation. So once you have done that, then you can use that data to help establish a margin. And a margin is something that you apply to your result when setting your environment that gives some confidence that you've captured the reasonable range of amplitudes that could exist for that particular location and environment definition. And it's a highly debatable topic, and there's different ways to quantitatively or qualitatively establish those margins. But I strongly believe that if your test specimen and simulation results and environment definition process has correlation like what we have shown here, that you can qualitatively establish those margins at a reasonable level of perhaps something like 6 dB, 3 dB, depending on the amplitude you're looking at, and be able to justify use of that kind of margin. One of the benefits of using simulation is that you have a more detailed mechanism for understanding current distribution within your fuel system. And this would apply for any area of the aircraft that you're doing evaluations. That within testing, you can accurately inject current, accurately include a probe for a particular area, but within the simulation, we can get a holistic view of how that current is behaving over the entire specimen that you're analyzing at all points in time, whatever you're specifying. And so what I've shown here is some detailed current maps for ribs that have direct injection onto them. On the left-hand side, there's a current entry into the fastener. So this is our fastener strike scenario where current is being injected into the rib and fastener and skin all at the same time. And this is sort of a evolution in time with 6 microsecond, the peak double exponential time being the top image, 30 microseconds for the middle image, and then 270 microseconds for the bottom. And basically what this means is for metallic fuel structures, metallic skins of your aircraft, it takes a while for the energy to diffuse inside and really get to all of your components. And the one on the right-hand side here is when we had the current injection onto one of the brackets mounted to a rib on the leading edge. And here's just another snapshot showing that current mapping along the rib. And within the simulation, you have the ability to map this profile, make an animation of it, or in a more detailed way, understand what your distributions are like throughout your entire rib. Now, anybody who's done current injection onto fastener knows that when you may have current flowing down your struck fastener and then back up the neighboring fasteners. And that kind of behavior could be understood in a very detailed way within your simulation by doing this kind of analysis. So in summary, the way we've approached this demonstration for the KART program is such that the data we have will be made publicly available, both from the testing and from the simulation standpoint at some time. And we feel that by using a test approach to understand current distributions on a wing structure, and then also simulations, this gives you by far the best understanding of what the fuel system lightning environment will be like when you have to go and establish your injection levels for your coupons. And so this is the recommended approach as far as we're concerned when you have to do this type of evaluation. And some additional benefits of the simulation are that once you have a specimen available, you may have a limited amount of time or scope that specimen is available to do the testing. And if you have a simulation model to accompany that testing, you can fill in any gaps that may exist within the test capability. If you have an interface between a rib and a skin, it may be that you cannot insert a CT probe around that particular shear tie. You may not be able to insert a Rogowski coil. Or be able to analyze what a current is like at a particular location. And if you have a high confidence in your simulation model, you can use it to analyze places of the fuel system that you absolutely cannot achieve with testing alone. And so I think that's a huge benefit of the simulation. And then one last one is that if you've done all of your testing, you're completed, and you have a simulation model to go with it, say you have to go back and change the design in some way, do you have to go back and retest it? Well, if you have a simulation model, you can use that as support for establishing that environment in the absence of testing. And that is an absolutely huge benefit of having a validated simulation model. And that's all I have to say about that. And I think I'll pass it back over to Billy now, and he'll give a summary of the work that's been performed and discussed today.
Yeah, well, thanks, Cody. I think that last point that you hit on was really important, is the ability that once you have the model developed, okay, you're able to go back and make changes in simulation to see, well, what happens if I do this, or what happens if I do that, where you don't have to drag the test out there and keep doing that. The other thing that this really, as I said earlier, it really did a tremendous amount for validation in my mind in regard to the modeling when you have really good data. So people say, well, what use is this data? Well, the data is extremely useful overall, it shows you how the program flow should go to try to do this, because with 25954 today, you cannot certify the airplane from a clean sheet standpoint without modeling. It is not possible to determine the current distributions around fasteners without the detailed modeling. So you cannot certify. Okay. And that's a little bit different than what we've lived with lightning certifications in the past. Yes, modeling has been a very powerful and useful tool, but it hasn't been required. That is the difference with 25954. Now, as we move to modifications, we move to doing STCs and things like that, I believe this data can be utilized to help supplement your analysis to where you wouldn't have to go run so many detailed tests, and maybe not any at all, depending upon the numbers. So I think this program has been extremely successful in regard to show how industry and research like WSU NIAR can come together for the benefit of industry and the benefit of the regulatory agency to show, hey, we can work together and how do we solve these complex problems. So we've done this for metallic skins and primary structures. We have yet to do it for composite skins. I believe it'll get a little bit harder, as Cody didn't really reference, but it will be harder for composites because it is not homogeneous. Okay, current does not flow the same way. The diffusion is directly correlated to the resistance, as Ernie just got through telling me again. And as a result of that higher resistivity of the composite structures makes that diffusion a lot quicker. And so it is a different animal. But we are trying to establish a sparking threshold database for construction and fasteners to help support industry. As I said, this is a very expensive rule to show compliance to, so we're trying to not make everyone reinvent the wheel each and every time. So we're trying to develop that database. We're trying to possibly expand that database of fasteners for the usage of industry to expand the usage of sealant, whether it's sealant caps, whether it's some sort of, I can't think of the name of those caps that are utilized.
Seal caps.
Seal caps, but those also can be utilized to help meet the requirements of fault tolerance. When the rule first came out, it was a dual fault tolerance, and in certain areas like fasteners, that's unattainable. So with that, I want to leave time to ask questions, but we do have plans to continue this. NIAR and EMA have a very long and useful or very long and fruitful relationship with one another, and we continue to build upon that. And I believe that if you have issues with this, NIAR in conjunction with EMA possibly could help you. So we're here, and that's really NIAR's mission, is to try to improve and work with industry, and not just, we're not a standard laboratory where you come and run a test and we give you the data. NIAR is here to help benefit industry. So with that, I'll turn it back over to the moderator and allow her to then ask questions if there's any out there.
Thank you all for that informative webinar. Now let's get to some of the questions that we've received. So first is, do the simulation approach and validation activities also apply to aircraft and composite structure?
Yeah, absolutely they do. And Billy mentioned it, that composites are in the works and plan to expand beyond the work that is done already. And there are certain considerations that may be different within the modeling and validation approach for composites, but in the principle, the way that you build your geometry and the inductive representation, the way you establish your resistances is similar between the two. And so you would go about doing that development process and establishment of your parameters in the same way. And certainly it doesn't behave exactly the same way, and your contact resistances may be different, but the approach would be very similar between the two.
All right, next question is, why are the coupons staggered the way they are?
Okay, this is Ernie. I can answer that question. Sparks, what we're testing here is the rivets, the fasteners. We wanted to eliminate any other possible interference with that. So what happens is sharp corners, like the corners of the coupons, and sometimes sharp edges, they like to arc and spark. So we staggered those coupons because if you line up a sharp corner with a sharp edge, there's a chance that it would spark instead of the fastener and interfere with our testing. So that's the reason we did that.
Yeah, and we're trying to ensure that the current goes through the fastener. So we're also using differential probes to look at that voltage drop between them. So in order to hook those together, as Ernie talked about, we have a phase surface there. So we're trying to connect, and we typically prevent contact. Those surfaces are coated, and so the only way current can go is through the material, is through the fastener.
All right, thank you. Next question is, how do you foresee this data being utilized in the future?
So as I spoke about, we're attempting through the SAE Lightning Committee, there's an ARP recommended, approved, whatever it's called, Aerospace Recommended Practice 6205 that is going through the process of approval within the SAE committee. It is hopeful that this data will be referenced within that document, and if it is, then it becomes public domain, and the utilization of that data for certification is accepted by the FAA. So the way to use this is not just directly from similarity, because again, it was not conformed through your process, but all of these were conformed through a company conformity. They all had an 8130-9 on them, not an 8100-1, but we tried to maintain that. We had multiple companies build the test articles, so we had a sampling and a spread of that, so that from a probability standpoint, we get some statistics. And I believe that they utilize standard techniques. So the hope is that certainly from a metal standpoint, most metal wings, this problem is not just a metal wing or a composite wing, it is a wing problem. And as Cody talked about, the current distributions and how the current reacts within the materials is somewhat different, but the overall aspects are basically the same. How does current flow through? How does it go from fasteners? What's the sparking threshold? How do we get fault tolerance? So the usage of this data, for nothing else, gives you a full idea of how you go from here's the requirement, how do I build up? How do I do the fasteners? What type of faults are we looking at? How do I then correlate that and compare and come up with some sort of validation for my software modeling? So that's how I see it happening. And the same will occur for the composites. Hope I answered that question. Cody, do you?
You said it very well, Billy. I have nothing to add.
All right, I think we have time for one more question from William Beasley. Your presentation has been very impressive. Are you assuming in your tests that the aircraft initiates the lightning?
So that's not really a question for this, but most aircraft trigger lightning, and therefore there was a study done several years ago by Boeing actually that looked at the size of the aircraft versus occurrence of strikes. And as the size of the airplane goes up and as the ability to enhance the electrical field, it's more likely to cause triggered lightning. Because say what you want to about pilots, they are smart enough not to fly directly into thunderstorms. So typically, most airplanes are struck, they trigger that lightning, or lightning is occurring and they divert it, called a hybrid, but it's really the same. Sometimes you get struck with intercloud lightning because you fly into it, and again, there's a charge center within the cloud and you trigger that and cause discharges. Or other times you can be flying quite a ways away from the cloud center, but you perturb the electrical field and cause a cascade effect that triggers the lightning to you. So I hope that answered the question. This assumes the airplane is struck and currents flowing through it.
Yeah, the only thing I'll add is that whether or not the aircraft initiates the lightning, there's a set of waveforms that have to be used as part of the verification process, and that's ARP 5412 that tells you what those current components are. And that's what we used for establishment of the lightning environment, assuming that we had current component A for a wingtip attachment, or current component D for a fastener attachment is what we used for that.
Yeah, and those waveforms, this is Ernie, those waveforms were developed as a composite of both negative, positive, induced or triggered lightning. Yeah, Cody's right. The ones that were in the standard, the ones that we use for this test, are based on a composite of all the above. So
yeah, so you don't see, those are called idealized waveforms. So it has, rise time, it has peak amplitude, it has fall time, it has what we call action integral, the ability, to deposit energy on different surfaces. ARP 5415 contains the part that Cody was talking about, and how we get what we call waveform norms, and how do we go from what we measure and take off the airplane from a test, and then develop standardized test waveforms to test the system. So all of those ARPs are listed in an AC 20-155 that allow you to use those ARPs as advisory material. So when you tell the FAA, I'm going to use AC 2155 to help certify my airplane, they understand that the ARPs are acceptable guidance material.
All right, it is time to conclude this session. As a reminder, any questions we didn't get to will be addressed via email. You will also be receiving an email from us with a link to the recording of this presentation, as well as the slides. If you have any questions about a particular section, please feel free to reach out through the EMA3D.com website or through our email. Thank you for your time and attention, and have a great rest of your day.